Good afternoon, everyone. I'm Jiao, a PhD candidate from University of Louisville. Unfortunately, Yunfei cannot join us today, so I will be the representative for the presentation. Yunfei is a PhD candidate from Shanghai Jiao Tong University. The paper title is Exploit both SMRAT attributes and NAND flashware characteristics to effectively forecast SSD-based storage failures in clusters. From now on, I will present from his perspective. Here's the outline, and I will introduce the work in 5 parts. First, I will present the introduction. Nowadays, to satisfy the performance demand in HPC clusters, SSDs are widely used as an alternative to HDDs. However, the increase in storage density comes with a trade-off of decreased endurance, and the prevalence of SSD failures poses a new challenge to overall HPC reliability. Here's a figure to show a hardware failure breakdown of a data center. We can see that the hard drives even takes over 62% of all failures, so SSD failures need to be noted. These failures bring significant penalties such as maintenance cost, data loss, service and availability, and extra. If SSDs fail in a cluster, they need to be replaced, but it may lead to a potential downtime. This will significantly impact the overall operational cost of the cluster. Also, when the SSD fails, the data stored on that drive is at risk of being lost or corrupted. Current data redundancy methods can provide the reactive fault tolerance in modern systems, for example, the replica and eraser coding. However, the cost of recovering lost data can be substantial and may induce the loss of productivity, even lead to service collapse. Therefore, instead of just relying on reactive data redundancy, it's essential to predict SSD failure in advance to proactively perform fault tolerance or maintenance. This figure shows the logic diagram of how to predict SSD failures in advance. Usually, a failure prediction sliding window is adopted upon the SSD monitoring data, such as the SMRAT logs. The conventional SSD failure prediction are usually based on SMRAT attributes using machine learning algorithms. However, the prediction performance of these methods reaches bottlenecks, especially in the emerging NAND flash type, such as the 3D TLC SSD. We have tried to reproduce the state-of-the-art SSD failure prediction models, but we found that the prediction true positive rate is even less than 70%. This is not acceptable. This makes me pause and consider, is it sufficient to rely solely on SMRAT data to predict SSD failures in our data clusters? Well, the SMRAT attributes offer valuable diagnosis insight. Do they truly paint a comprehensive picture to efficiently forecast the potential failures? So to answer this question, we investigated the Spearman correlation coefficient rank of the SMRAT attributes with SSD failures. As shown in this figure, we show the top 11 attributes correlation coefficient. We found that only 2 attributes have more than 70% coefficient rank, which is the power on hours, the wear leveling count. The other are less than 3% or even less than 0.5%. Thus, we can see that the answer is no. The SMRAT attributes are not enough. It may bring bias to the learning model, hurt the prediction accuracy, decrease the true positive rate, and increase the false positive rate. This becomes the main limitation. Besides, there are several other challenges in disk failure prediction. This figure and table give us an example of facing the problem, including the datasets imbalance, the minority disk models that do not have enough samples, and model aging. For example, the first MC2 SSD failure occurred over 2 months after the first MC1 SSD failure. If a predictor had been trained prior to this event, it would have performed poorly in predicting the MC2 failure due to insufficient learning of specific features. To overcome these limitations and challenges, our work achieved the following milestones. We gathered and analyzed over 20,000 SSD manufacturing self-test logs, extracting LUN-specific aging back data and observing distinctive feature patterns. Moreover, we introduced our innovative SSD failure prediction approach, the Aging-Aware Pseudo Twin Network. We are the first to integrate SMRAT attributes and MST logs to achieve effective long-term failure prediction. Then we adapted into an online learning framework for the practical implementation. Finally, we conduct several experiments to evaluate the performance of our proposed approach. Next, we'll introduce the preliminaries. Let's revisit the SSD failure key impactors. The figure on the right shows the internal structures of an SSD. So we can see that NAND flash serves as the storage media for the SSD, which is the root cause of SSD failure. From the literature study, we conclude that the key factors impacting SSD reliability are listed here, including the device level, NAND flash wear characteristics, SSD age, flash tap, and lithography and capacity. Plus, Mesa's team proved that the wear characteristics of the NAND flash are the most crucial factor. Besides, let's then check out these two graphs. They are from Mesa's team research. They look at the failure probability of the SSDs with a 3D TLC and MLC flash over time in real-world use. Their finding is pretty interesting. The SSDs with the same kind of 3D TLC flash and similar storage capacity tends to fail at the same rate over time. It doesn't really matter what brand or model the SSD is. However, due to the non-transparency firmware embedded in SSD controller, it provides statistic values of the SMRAT attributes rather than the device level NAND wear information. So how can we get that wear data? We collaborate with in-house team SSD manufacturer, try to explore the SSD NAND flash wear characteristics via firmware customization and extract this data as the specification in product document. We collect the data in two steps. Step 1, we perform erase and program on SSDs in the first several loops to reduce the false bad block marking from the annealing effects. Step 2, we perform erase, program and read operation to erase all blocks in chunk, and then program them starting from page 1 to the rest of pages. We repeat the above operations until all pages of all blocks in this chunk are fully programmed. During the read operations, the bit error counts of each 4K data frame is tallied as a histogram for each loop. For instance, if a data frame contains no errors, the process increments the back bucket number of 0 bits. Then we extend this logical progression and finally obtain the SSD aging back histogram data. To make it easier to understand the aging data, we turn it into a heat map. This figure shows a fragment of a heat map on aging back data upon a chosen LUN from an SSD. Basically, we'll use different colors to show the size of each little bucket in the histogram. So the brighter the color, the bigger the value in that bucket. It's worth noticing that there are the spikes around the 30 PE cycles, since the earlier defective blocks that have intrinsic weak LUN are wearing out in these cycles. This is consistent with the conclusion in our previous literature study. This type of non-flash aging data serve as important features because there's a strong correlation between back data and ECC algorithm that manages the correction of raw bit error occurring throughout the entire lifespan of the SSD. Because if the back surpasses the hardware ECC threshold, the data may be corrected by soft decision ECC, but it's highly to fail. And then how does the percentage of LUNs change over different PE cycles? This example shows how LUNs in a drive age over time, with 5 different PE cycles shown here. The area under the curve represents the cumulative percentage of LUNs, and the red vertical line marks the halfway point. In this figure, you can see that as the PE cycles increases, the distribution of the maximum bit error count shifts to the right. This means that the drive is more likely to fail as it goes through more PE cycles. After our discussion, we might wonder how we can use back data and SMRAT data together to predict the SSD failures. Let me explain the design. So this figure describes our proposed framework for SSD failure prediction. It contains 5 parts, including data collection, SMRAT aging sampling module, the model training process, online prediction, and the iterative training process. SSD back data here is obtained through the firmware's API interface, serves as a representation of SSD's internal wear patterns under different PE cycles. Unlike SMRAT data, SSD back aging data is not collected in real time. It's gathered in an offline environment through wear tests conducted by the SSD manufacturer's in-house team at the firmware level. SMRAT data represents real-time operational statistical information obtained during SSD runtime. These 2 datasets exist in different dimensions and cannot be directly combined. So we built an Aging-Aware Pseudo Twin Network called APTN to solve this problem. This APTN network contains 4 parts, including input layer, subnetwork 1, subnetwork 2, and output layer. The input layer contains a SMRAT aging sampling model. It normalizes both the average power on hours information in SMRAT data and the average PE cycles in aging back data. Here's the SMRAT time series and the aging PE cycles series derived from the distinct sets of SSDs. But it doesn't matter, as we discussed before, because they are under the same NAND flash tab and share similar capacities. After this sampling, we get a large number of SMRAT or aging sample pairs. Then these data are forwarded to the following subnetworks. The SMRAT data is forwarded to the subnetwork 1, a multiple layer neural network, because the SMRAT data has stronger significance in their spatial feature. And the SSD back data is forwarded to the subnetwork 2. In APTN, which is a LSTM network, that is because aging back data preserves both short and long temporal patterns, and LSTM is good at abstracting the important features in such type of data. However, the SMRAT attributes and aging back data are from different dimensions. One is from real-time system logs, and the other is a type of static characteristics. They are even in different shape and dimension. Therefore, they cannot be compared directly. So we project these 2 types of data into a high sparse space and compare the similarity by computing the error to norm distance. We then compare it with the distance threshold to identify the SSD is healthy or soon to be failed. However, the prediction accuracy fluctuates when the output distance is close to the present threshold and meets the correct identification. To address the problem, we add a random forest-based adaptive discriminator to dynamically adjust the decision margin threshold to compensate the threshold fluctuations according to the characteristics of the specific real-time SMRAT sample. So our design is all set now. To prove the effectiveness of our work, we conduct several experiments for prediction performance evaluation. The dataset and compared models are shown in this figure. The dataset we used is already mentioned before. This is open sourced on Alibaba Tianchi database. The objectives we analyze are 3D TLC SSDs. We reproduce the state-of-the-art multi-view random forest, logistic regression, k-nearest neighbor, decision tree, neural networks, and their online adaptation algorithms from the related work. But please keep in mind that these compared networks are only relying on the SMRAT attributes. The first experiment shows the predictive performance comparison with the existing methods. We use TPR, FPR, F1 score, and AUC scores as the key metrics for the evaluation, which are essential for system maintenance like SSD replacement. We can see that our proposed method, even in the long-term prediction, like 30 days look ahead or 120 days look ahead, the performance degradation is really tiny. This is meaningful for the proactive maintenance decision making. Then we discuss the sensitivities. First, we replace the subnetworks in our APTN to prove that this combination is optimized. The alternatives of subnetworks are shown in the table from the experiments results. Our proposed APTN with neural network and LSTM performs the best in both short-term and long-term look-ahead prediction by 13.5% improvement on average. Then we talk about the sensitivity too, on and off the RF-based adaptive discriminator to see whether the discriminator design is necessary. In the end, APTN achieves lower FPR with 23% on average and get F1 score and AUC score of at least 4% higher than APTN without RF-based discriminator. APTN benefits from a distance-based similarity comparison and a sample pair pooling mechanism, which naturally avoid these biases. We show how well it predicts SSD failures for the MC2 drive model among offline models as of 2018, March 27th, and how it improves with the online learning framework. As you can see in the graph above, all models almost fail because there are very few MC2 samples at this point, making it hard to learn their characteristics efficiently. After implementing online learning, our APTN method rapidly gets into high and steady predictive performance in 30 days look ahead. The TPR and F1 score of APTN are higher than other methods by 40% and 30% respectively. Finally, we use the cost MTTDL metric, which is the economic analysis metric, and evaluate the reliability and availability of the system based on different methods. MTTDL is the mean time to data loss. C and CB represent the associated cost for misclassifications. Mu is the inverse value of MTTR. From this table, we can see that our proposed APTN improves CMTTDL approximately from 2.5 times to 15 times, which significantly improves the reliability of the storage system at a lower cost. Finally, we can draw the conclusions. In conclusion, we learn from SSD supplies and prove that until now, SSD smart locks provides a limited number of attributes that may be useless. Therefore, solely relying on SMRAT for emerging NAND flash-based SSD failure prediction is not enough. Fortunately, we can use SSD NAND flash wear characteristics as an important failure prediction indicator, and combine with SMRAT to get the high TPR and low FPR SSD failure prediction. And we think this work may bring a good insight to this area. And SSD manufacturers could potentially include NAND wear characteristics in their product specification documents to help or guide SSD failure prediction. That's all for today's presentation. Thank you for listening. If you are interested, please read our details in our paper. Thank you.